Let's take a look at this problem. I have a 640-meter race between two cars. Car A accelerates at half a meters per second squared for 10 seconds, and then keeps a constant speed. Car B accelerates at 0.4 meters per second squared for 20 seconds, then maintains that constant speed for 40 seconds, and then decelerates such that it is going half its maximum speed when it finishes. Which car wins the race? Well, as always, I'm going to start with a picture. I have two cars, okay, they're starting at the same place and they're going to end at 640 meters, but how are they traveling these distances? I've got car A with some acceleration for some time, then constant speed. Car B has an acceleration, a constant, and a deceleration. This calls for an acceleration graph, at least, to try to get a handle on what's going on. Here's acceleration as a function of time, and I've identified 10, 20, 60 seconds as key times within the race. T sub capital T is the total time for each car. So what's going on with the blue car? So it has some constant acceleration for the first 10 seconds, and then it's zero for the rest, because it's at a constant speed. What about car B? So it has a lower acceleration for the first 20 seconds, then zero acceleration for the next 40 seconds, which is between then 20 and 60, and then it will have a negative acceleration for the rest of the time. What does that tell me about the velocity, though? Car A accelerates at 0.5 meters per second squared, so its velocity graph will have a slope of 0.5 meters per second squared for the first 10 seconds, and that tells me then how fast that it got, because the slope is the rise over the run. Also, if it starts at zero, the final speed is just going to be the acceleration times the time. And then it will stay 5 meters per second for the rest of the way. What about green? So green accelerates at 0.4 meters per second squared for 20 seconds, which leads to a top speed of 8 meters per second that you can get from rise over run for the slope of 0.4, or just 0.4 times 20. So now it stays that speed for 40 seconds until t is equal to 60, and then it starts to decelerate. And since I found the top time already, I know that it's going to decelerate to 4 meters per second when it crosses the finish line. Well, where to go from here? Now I have a set of equations that I've used for systems of constant acceleration. But the acceleration is not constant here. There are, in fact, 5 separate regions of constant acceleration. Car A has 2 regions where the acceleration is constant, but I have to break car B into 3 regions where the acceleration is constant to be able to use my constant acceleration equations. And if you want to take a look at just what that entails, I've broken it out for you. Here's region 1 for car A. I can say its initial time is 0, its final time is 10 seconds. I know the initial position. I don't know its final position. I've identified that as x sub a1, initial velocity. I'm assuming I'm starting from scratch. I don't know the velocity yet, but then an acceleration of 1/2. If I were to set up the second stage for car A, then its initial time is the final time from before. It has some total time for car A. I don't know what that is. Final position is the end of the race, and it's at a constant speed with 0 acceleration. Now the third stage, which is the first stage for car B, some initial time, some final time I know, initial position, I don't know the position it ended up, and starting from scratch, I don't know what its final velocity is, I just know its acceleration. The second stage goes between these 2 times. I don't know its location, but its velocity is the same as before. And then the final stage goes between 60 and the final time when it crosses the finish line. I don't know. Where it starts is where it ended before, and it ends at the end of the race. The initial velocity is the final velocity from the previous stage. Its final velocity is that divided by 2, and I don't know what the acceleration is. So there's 5 different phases of constant acceleration. Well, how would we go about solving that? Well, we have these equations that can be used for each phase. We would have to do that 5 times. I've counted 8 unknowns in this set of data, so presumably we could find 8 independent equations out of all of those phases from which we can solve for our 8 unknowns. Well, maybe I don't want to do that. Let's go back to our velocity graph. Here's velocity versus time for car A. And what else do I know? I know it's a race, so I know that the total distance the car went is 640 meters. Well, what's the relationship between that displacement of 640 meters and the velocity versus time graph? It's the integral of the velocity over time graph. And the integral is simply the area under that curve, which is just one triangle plus a rectangle. The area, which is 640 meters, is 1/2 the base 10 times the height 5 of that first triangle, plus the area of that rectangle, which has a base of the final time minus 10, that's the length of the base, times the height of 5. And that's it. That is one equation, one unknown, and I can solve it immediately. That's equal to 25. I've multiplied out the 5 times the total time minus 50. 665, then divide both sides by 5, and the total time is 133 seconds. And that's it for car A. Let's look at car B. It's more complicated, but not that much more complicated. And the area under it also has to equal 640 meters. I have a triangle and a square and then a trapezoid. What are those areas? 640, here's the area of the triangle, 1/2 base times the height, 20 times 8, times the area of the rectangle, which is base times the height, and the base is 40, the 60 minus 20, and the height then is also 8. Now you may not remember the area of a trapezoid, but that's a Google click away. It's 1/2 the base, which is this time interval, times the sum of the two unequal sides. I already know those as 4 and 8. So look, I have one equation will tell me that final time difference, which I just add to 60 and I'll be done. The triangle area is 80, rectangle area is 320, and then this last term gives me 6 delta t. Subtract 400 from 640, I get 240 is equal to 6 delta t, or delta t is equal to 40. The 40 is the last time interval, added to 60 gives me 100 seconds, which is the time car B finished, which is less than 133, so car B wins the race. And I hope you have gained an appreciation for the power of graphical methods. They can help you understand a problem, they can help you check your work, and in some cases, they can help you solve problems overwhelmingly more quickly.